We are in this work package that serves the AI and machine learning needs for all the other work packages. Now, for today, following up from the panel discussion that we had just now, I was talking to you about learning with less data and less compute. And what that really means is resource-efficient machine learning, right? This is our team, right? We work with Daniela, Alex, Alok, and the postdocs and students that we have in this team. I'm going to share with you two separate ideas and research that we have been doing, right? But before that, let's talk about some of these challenges with general machine learning. Two major things to bear in mind. First, data, right? You need data to learn. Second, you need a platform that can compute what you have learned, right? So you see over on this side, we're talking about both the quantity and the quality of data. And on this side, you need massive compute, right, to be able to process the data so that the model can learn. Now, these are some of the other general concerns that we won't be addressing for now. Right now, we're going to focus on the top. Specifically, we ask ourselves, how can we learn with less data? How can we learn with less compute? So you're going to see in the first effort that we are focusing on learning with less data. The second one will be on less compute. Now, these are some of the publications that we have worked together towards. Now, the first idea, maybe I should jump to this slide first, right? The first idea is really about how we can learn with less data. Now, usually you're going to find, even for LLMs, right, you're going to need massive amount of data. But is it possible that, in fact, this huge amount of data can be compressed into a small data set such that it can achieve a comparable learning performance? Now, this is one of the research that our group has done, right? Imagine the case where this is a huge amount of images, beyond 200,000. But interestingly, right, even though this 200,000 images can give you 95%, if we distill to just these two images, it can already achieve a comparable performance of 92%. Now, this is one of those technologies that, or what we call distillation, right, that allows us to compress data to a small size. Now, imagine that with this data set, you can actually hand it over to several different groups who wants to train the machine learning model. And this is actually a good thing to sell, right? Now, the second part is on what we want to do on achieving less compute. What are we looking at? Now, the problem that we're interested in is one where you have a system of components. Now, in the real world, it's not reasonable to expect that all you need is a machine learning model. Instead, what you really need is to handle a system of various components, right? As an example, if you think about robotics, in robotics, usually in a company, you're going to find that there are different departments, each with developing a separate component. You have a department that does perception, one that does planning and decision making, and one group that does the control. Every now and then, they will meet together and see how they can all fit into the autonomous vehicle, right? Now, however, if each of this department tries to optimize their respective component to the best, putting all of them together, the system may not perform optimally, right? The analogy is that, during my time when I was younger, Real Madrid is a team that's full of superstars, right? But it's not very often that they always win Champions League. So you can imagine that, a system that has components that give you the optimal system performance is what you really need. But that does not amount to the fact that every component needs to perform optimally, right? So this is something to bear in mind. Now, the same goes for, in recent years on prompt engineering, right? In fact, prompt engineering to many people you would think of it as manual, a very manual task, but in fact, it can be automated. And this prompt engineering pipeline can also be thought of a system of various components. Now, what's interesting in our problem is that, of course, there are also components that are black box to us. The most interesting one that is appears will be that of healthcare. To us, doctors and clinicians are black box components because we don't really know what's going on. Yeah, but I hope that I've given you enough examples of the fact that in the real world, it's really about a system of components, okay? Now, so what we do here is that we classify this as the auto AI problem, where there are many components, however, we want to jointly optimize all of them so that we can get the optimal system performance, right? That's what we want to achieve. So, like I've mentioned just now, right, training a single model with respect to data is what the machine learning researchers usually do, but in the real world, the system has components and we need to jointly train them, all right? Okay, now these are two major challenges that we face. First and foremost, if you're thinking about a system, how is that even scalable? That system will have millions to billions of training parameters, right? Especially if you're thinking about multiple machine learning components within the system. That's extremely high dimensional. Now, of course, you know, in our field of machine learning, there are gradient-based methods that start to climb, right, along gradients to the optimal performance. Now, however, remember in our problem, there are the black box components that are the doctors, right? So in this manner, it is not possible for us to use those kind of approaches. Now, on the other hand, right, because of these black box components, it is not feasible for us to write down in mathematical form what the entire system is about, right? As a result, it's going to make it really difficult for us to optimize using gradient-based approaches. And what happens, of course, is that for this kind of black box problems, there are also optimization methods called Bayesian optimization or black box optimization methods for those kind of problems. However, for those algorithms, black box optimization algorithms, they usually cannot scale to very high dimensional, right? So putting these two challenges together, it's no wonder, right, that the existing classes of algorithms, they can't really tackle a problem like this. So this is a good contrast, right, of what's going on. What would happen in the industry, right, usually, is that when you have a system of components, each of the department will go ahead and train their components separately, right? This is what we call the local approach towards some optimality. Now, like I've mentioned just now, if you put all of them together, right, it may not perform optimally as a system. Now, on the other hand, there are global approaches that can reach optimality, but they are restricted to low-dimensional problems. So, our key idea, right, is the following. We ask ourselves, can we do a global to local design kind of approach, right, where there's a global entity that informs the local components what to do, right? Now, in order to do that, there must be some kind of grounding to a common language, right, between the global and local approaches. What is that common grounding? It is this auxiliary information in the machine learning community that we call the loss function. What does the loss function mean? It means how much are you losing by not learning well, right? So for each of this component, it's going to be able to report to this global entity, right? What is its loss, right? That is, what does it lose by not learning well? Now, with all these different losses, with respect to all these components, the global component, right, is going to tell each of these components what loss to try to achieve. And because of that, it's able to achieve the global optimality. Now, we have tried it on the prompt engineering pipeline. I'm not going to elaborate on that, but you know, in any research, we have to demonstrate that we are always better, right? So, right. So in other research we have done, right, we do automated prompt optimization. If you're interested, I can talk to you more about that. But yeah, this is a really interesting one. For example, you know, what other groups have found is that a very good prompt that they found would be, let's do it step by step, right? If you want to achieve good performance. However, we can optimize over them and get something better. What we got is, let's use our brain, right? That's something that's really interesting. Okay, so 3 takeaways to wrap up, right? One is that, you know, for the auto AI problem, like I've mentioned, there's a need to jointly optimize all the components in the system so that you get an optimal system performance. However, you can see that something like this is extremely challenging. I've described the challenges to you. However, this is also very prevalent in many problems. We have shown you a scalable way of solving that problem. Now, what's most important is always this. In any problem, you should always go in and take a look at the problem itself, see whether there's some kind of structure you can exploit, right? So that you can develop an efficient algorithm, right? That's the takeaway message. Thank you.